Hello, Run. I am Tom Ballard, the Guy, and welcome to Groundwater Talk Live. Today, our topic is economics of well modification. We're talking about well modification with respect to contaminants in water supply wells. And this is a topic that comes up a lot. The first option that most people think about is treatment, but treatment systems can be expensive. So we'll look a little bit at the alternatives to treatment and look at well modification as an option there. So that's really what we're going to explore in the show today. But first of all, let me say, if you get to the end here and you find value in this show, then please like, comment, and share. I answer all comments on the YouTube page and on LinkedIn, so and elsewhere that we stream this. So please do that if you find value in this, and I appreciate it. All right, so let's talk today. There are a lot of water wells out there, water supply wells that are impacted by various types of contaminants, and there's a real list here. We'll talk about that in just a minute. But the question is, if we're exceeding MCL for these contaminants, we're obviously going to have to do something to get our water supply back into compliance. And so the first option that most people turn to is treatment because that is the traditional method. However, we have some other alternatives that we'll look at today, and particularly well modification. In the right circumstances, it can be a great option, but we need to understand what those circumstances are, where it works, and what the comparative costs are, and that's really what we're going to discuss today. So let's dive in here, and kind of we'll go through this, and then at the end we'll go through the actual cost comparison and kind of see how these things shake out in terms of cost. So let me start off first with, talking about. I did mention that many wells are impacted with contaminants above the regulatory limits. The MCLs is usually what we're using. Different states have their own, like California, for instance, has their own MCLs that may or may not match the US EPA MCLs. But the regulatory. So when I talk about regulatory limits, I'm mainly talking about MCLs, whether it's state or federal MCLs. So a lot of wells out there, water supply wells that are supplying drinking water to folks, basically have contaminants in them that they need to deal with. And there are plenty of methods to dealing with this. And like I said, the treatment option is the one that most people think of first because it's the traditional method. And we have quite a variety of contaminants out there. We both have anthropogenic, which is man-made, long word for man-made, but anthropogenic and naturally occurring contaminants can be present in wells. So it's kind of a grab bag out there. We'll look at. Let me see here. So my slides aren't flipping here. So there we go. So probably what an example we look at, and I got a couple examples we'll look at here, and then we'll kind of list them off. But arsenic is the most common contaminant in groundwater wells worldwide. It impacts, for instance, in India, 25% of the water supply wells in India are impacted by arsenic. Certain parts of the country in the U.S., California, Nevada, arsenic is very common. As a matter of fact, in California, arsenic is the number one contaminant of water supply wells in California. So it's a naturally occurring. Generally, there can be anthropogenic arsenic out there that's but mostly 99% of the cases it's going to be naturally occurring. And it often has lithostratigraphic controls. And by that, I mean there's usually some lithology, uh, rock type that where the arsenic is prominent. And if you screen across that in a well, you're going to have arsenic issues. And so it can be arsenopyrite. There are a number of arsenic compounds that show up. There's a lot of chemistry to it that we're not going to get into. That's a topic for another day, is the geochemistry of arsenic. But suffice it to say that arsenic is a very common contaminant out there. most people just don't realize how common it actually is out there, but it is a fairly common contaminant. So, but the good news is because it is stratigraphically controlled, it can be a candidate for doing some relatively inexpensive techniques to control the arsenic coming into the well. So this is good. Nitrates, another big one, especially in the U.S., and it's a widespread contaminant in groundwater. It's usually anthropogenic in occurrence because it is mainly coming from fertilizer. There are also sources from septic systems, from feedlots. So nitrate sources are very important. We can actually do isotope analysis and determine what the actual source is, whether it's coming from manure, whether it's coming from fertilizer. That's a topic for another day also, but usually nitrates is going to be a shallow groundwater issue, and I would say that well over 90% of the situations that I deal with nitrates in, it's going to be a seal issue. There's going to be an inadequate seal or a degraded seal that's going to allow shallow groundwater that's impacted with nitrates into the well. The well may have been designed with a shallow seal that did not take into account the geology. So now you have a well that is in and it has an inadequate seal and you have nitrate issues. What do you do about that? So those are probably the most common ones, but we have there's plenty of examples. The PFAS, PFOA, that is a hot topic these days. That's showing up everywhere. TC, PC, and other solvents. Those are clearly anthropogenic, as is PFAS. Bacterial issues. We see mainly we're monitoring for coliform bacteria. Bacterial issues. We'll see a lot of those that'll be coupled with nitrates because what happens is it's another seal issue. It's shallow water coming or surface water coming into the well, bringing bacteria. Groundwater under the direct influence of surface water can have bacteria issues too. So that's another fairly common one. 1,2,3 trichloropropane is derived from the DBCP fumigant that is used a lot in agriculture. We see a lot in California, in the Central Valley of California. It's a big problem. Chromium 6 can be both anthropogenic and naturally occurring. So we all heard of Hinckley, California, the Aaron Brockovich story, and all that. That's anthropogenic. Came from PG&E, contaminated the groundwater out there. But far and away, the majority of chromium 6 issues are going to be naturally occurring. But it can be both anthropogenic and naturally occurring. We know there's plenty of cases out there of anthropogenic contamination from spills or some other source of chromium 6, as well as naturally occurring. Perchlorate, jet fuel, rocket fuel, is can be both anthropogenic and naturally occurring as well. It can show up in fertilizers, as a matter of fact, especially fertilizers imported from Chile in South America are high in perchlorates, and that can get in the groundwater. A really common one that's generally going to be naturally occurring is iron and manganese. And radionuclides is actually a bigger one than most people know. In California, for instance, it is the second largest category of groundwater contaminants and pretty much always naturally occurring. So people think of radionuclides and they think it's contamination from a nuclear source. Generally, that is not true. It's generally going to be naturally occurring, and so we can look at that. We can track that down and see where it's coming into the well from. So there are some tools that is kind of beyond the scope of our talk today for dealing with that. But that's a topic for another show, right? So. All right, so our options to deal with contaminants in wells is number one, go out and replace the well, and that's going to involve just abandoning the existing well and putting in a new well somewhere else to replace that water supply. So that's number one. That number two is a treatment system, and this is the one that most people think of is treatment systems. There are some treatment systems. There's a wide variety of treatment systems available that can do the trick. They can certainly do the trick, but they are expensive and they are an ongoing cost. So we'll look at that too. And thirdly, something that's becoming more common that people are looking at and kind of our focus here today, although we're really doing a comparative discussion, is well profiling and modification. So we'll talk about, yeah, and I've talked about that in other shows. But really, what we're doing is we're going in and characterizing the well. We're looking at the flow coming into the well. We're looking at the vertical distribution of the contaminants coming into the well. Remember, like I said, that arsenic can have lithostratigraphic controls. Nitrates can be shallow issues. So we'll go in and we'll look and see where these contaminants are coming into the well, see if there's specific zones that they're coming in that we can actually go in and modify that well to seal off those zones without substantially affecting the productivity of the well. So that's why we do the flow profiling and we do the vertical profiling of the contaminants, and then we do a mass balance to really look at basically, can we seal the zone off without substantially affecting the production of the well? So that's kind of the balancing act in well profiling, and we'll dive into that a little bit more when we talk about the cost. So let's first talk about well replacement, because this is certainly a viable option. It can be a good option if you have high levels of contaminants that is going to be very expensive to treat, or if they're evenly distributed throughout the well, which doesn't make it a good candidate for well modification. So this can be a good option. However, the downside is a new well, especially a municipal type well. You have a well that's producing 2,000 gallons a minute, 16-inch well, 400 or 500 feet deep, 800 feet deep. That is going to be very expensive to replace. So we'll look at the cost for that, but it can be expensive. And if you locate it, ways away, there's no assurance of success. We generally, can do pretty well, but we don't know if we're going to hit any unknown contaminants in the new well also, and we don't know how much water we're going to get. We should know, but until you actually run the test boring and do the testing, you don't know these things. So you can spend a lot of money and not get the results you expect. So we may not get the productivity quite as many gallons per minute as we had in the old well, and that becomes problematic too. And other factors can be land access and location relative to existing infrastructure can also be an issue. I mean, you need to be able to tie into your distribution lines or your storage system, as it were. So you need to have the land access, the easements, and be able to get that. That can sometimes be a challenge in a municipal area. So where do you go with that new well? Oftentimes, regulations say you can't drill a new well right next to an old well. There has to be a certain amount of offset, and some of these lots that they have the municipal wells on don't allow for that offset. So you got to move it somewhere else, and then you get into a little bit more of a guessing game. We do our studies and we come up with our best estimates of how much water you're going to get and if there's any contaminants. But until you actually drill the test boring, you don't know. So that's so there are pros and cons to the well replacement option, and like I say, it can be very expensive. It is a one-time cost generally. I mean, there are obviously maintenance issues, but the big part of the cost of a new well is upfront. So. And here's some factors we look at in new well construction. These all have dollar signs attached to them. You need to abandon the old well. You need to do property acquisition, which can be not only expensive, but it can be time consuming and challenging. So you do your site selection, your exploration, so your test borings, and you do your well location study. So we're really looking at the potential for contaminants, other wells in the area to determine, what kind of production we can expect from that well, and then design, permitting, plans, specs. You need to bid all that out. You're going to need to do some geotechnical survey. There's going to be legal and admin costs. And besides just the well itself, you're going to have the pump. And obviously, if you're putting in a line shaft turbine for a big pump, that's going to be expensive. But even a good submersible can be expensive. We have to have a pump house, usually some kind of protection for that. There's going to be engineering costs to do that. The infrastructure connections. How do you tie into your distribution lines to get it to storage or get it into your system, get it to the treatment plant? So there's going to be costs involved in that, and getting your electrical power drop. That can sometimes be quite a challenge. So there's a lot of things, and there's some intangibles. We may think we got a great property, and we do our study and find that there's some contaminants that could affect our well, and then we're not doing ourselves any good, so we need to look somewhere else. So there are some intangibles that get factored in here that you can't really put a price tag on here, but they do come into play. All right, so and like I say, the drilling rig access can be challenging for new wells. This is a for a decent size municipal well, and you can see how much room this actually takes up to drill this. They got a sound wall back there. They have the mud tanks, and so it can take up some room. So you got to have some room to get in there and drill. You can't just squeeze it on a little corner lot somewhere. So this can be challenging to get the room and the access to get in. All right, so treatment systems, moving on to treatment systems. Treatment systems are available for a wide range of contaminants. Pretty much anything you can think of has some type of treatment system that is available, and it can be highly effective at maintaining your water quality, getting it to acceptable levels, getting your contaminants below the MCLs. Now, obviously, there's some maintenance involved in that and constantly monitoring and checking, so there's ongoing costs. But treatment systems are certainly a viable option, but they tend to be your most expensive option. Not only the capital costs, but the ongoing costs. So that's that's kind of the downside to treatment systems. But they are a viable option, like I say, and you can treat all kinds of, depending on what you have. There's a treatment system available for that. It's just how much it's going to cost you to install it and run it. So relatively high capital cost is going to be the hallmark of a treatment system, but it's the gift that keeps on giving, because it's going to require ongoing maintenance for equipment, changing out valves, chemical feeds, depending on how you're doing it. If you have things like, if you're using a reverse osmosis system, what are you doing with the brine? How do you treat that? There's costs involved in that. For ion exchange system, for instance, you got to change out the ion exchange resins and deal with that. Going back to the reverse osmosis, you got to clean that screen, flush it, and then you got to deal with the brine. So it can be expensive. Other things require some back flushing, dealing with the wastewater. So you got to pump it to waste and deal with that. So a lot of maintenance goes into that. And the other thing you need to consider too is, depending on the type of treatment system you have, it can often require a higher level of operator certification, which adds to the ongoing costs. If you have to go out and hire a new operator that has a higher license, a level 3 license, for instance, as opposed to a level 2 that you had before, well, this can definitely add to your cost, because now that's an ongoing cost, because you need that operator there to maintain the system, and that's part of the requirement. So you can see that we not only have the capital and costs involved, but ongoing costs. So it as long as you have the treatment system, you're going to have these ongoing costs, and over time things are going to break. You're going to have to replace them, and so and and then the treatment system can eventually become obsolete. You may need to replace large components of it. So there is a lot of ongoing costs, capital costs, and ongoing costs that it's involved in treatment systems that really makes it the most expensive option. We'll look at the costs here as we get down to the end, but that's the thing to take into account with treatment systems. So even though that's the option we jump to right away, and it's the default option, and the regulatory agencies love to see treatment systems because it gives them something to check on a regular basis and review the reports, and its job security. There are potentially other options out there for that. And as I said, treatment systems can be complex. They can vary widely in costs. You need to have room to put them in there. So the land issue that I talked about with the replacement well can certainly be a consideration for treatment systems, because you have to have somewhere to put it. And depending on the type of system you have, it can be a pretty decent building. You got to have an engineered pad to put it on, and you have to have all the pipes and valves and everything that goes into that. So there can certainly be some costs involved in that, and so, but because of the types of, and I'll show you here just a minute the wide variety of systems we have out there. And as you can imagine, the costs vary pretty widely. So you can go from a routine like green sand filter for iron and manganese, all the way up to reverse osmosis systems and combination type systems that can really, bump your capital costs way up, and your operating costs as well. So these are just some of the options out there, and this is not an exhaustive list. We can see we got everything from granular activated carbon, packed tower aeration, multi-stage bubble aeration, anion exchange, cation exchange, biological treatment, reverse osmosis and nanofiltration, adsorptive media, ultraviolet and advanced oxidation processes. You have caustic feed, you have phosphate feeds. Some of these are a little more specialized, but and there's other ones out there. So you can see there's a wide variety. These are all going to have different costs attached to them. So it can get fairly complex. And if you are looking at costs, there is and I'm not going to go over this in great detail, but there is the USCA, EPA water treatment cost models that are available that actually have some pretty detailed explanations and spreadsheets that look at all these different treatment systems and allow you to come up and estimate costs for not only installing these things, the capital costs, but also the ongoing operating costs. So I put the URL here so that you can go to that page. It's got a lot of good information, and if you love spreadsheets, this page has a lot of them. So we'll probably visit this in more detail and in a future show. It's got a lot more information than we can really dive into here, but this is kind of what the front page looks like here. And it's a great source of information. They keep it updated, and if you're interested in estimating your costs for a treatment system, this is probably going to have some information you need. But be prepared for the level of detail you're going to be looking at, because there's a lot of detail that goes into this. So that's because treatment systems can be complex, and there's a lot of moving parts and a lot of associated costs. So, all right. So we've talked about well replacement. We've talked about treatment system. Now let's go on to well profiling and modification. I get involved in this a lot because it's a good tool out there when it's appropriate. Now, it's not appropriate for all situations, I will tell you that. But as I mentioned earlier, profiling to identify, you're doing profiling first. It's a two-stage process. So you're doing the profiling, and then you're doing the modification. So profiling involves identifying the flow characteristics of the well. where is the water coming into the well? What are our aquifer zones, and how much water is coming into those particular zones? So we'll go in and we'll profile those. There's a number of different techniques we're not going to talk about today to do that, but you need to know if you're going to modify the well, you need to know how much water is coming in what zones, because if you're going to be prepared to seal off some of those zones, you don't want to seal off 100% of your production, because obviously that's not going to work. So, but clearly that's an extreme case. But if you're losing 20 to 30% of your production, that may or may not be acceptable. So you need to do the mass balance to figure that out. So the other component of the well profiling is actually using a discrete sampling technique of some sort to build a vertical profile of where the contaminants are. And oftentimes we can match that up then with the drill log and any geophysical logs that we have, and we can determine what particular lithostratigraphic units may be associated with the contaminants. So this is often the case with things like arsenic, like I mentioned earlier. Nitrates tend to be shallower in the well, so that's going to be an issue of modification that's going to involve dealing with the seal, but we need to look and see where it's coming in. So we don't always have adequate well logs, and well log quality can vary all over the place. I like to look at the well logs and kind of match things up so we know what the well construction is and what the geology is. But sometimes you need to go back. If you have an e-log, that can be very helpful. Sometimes part of the profiling can be involved doing some geophysical tools so we understand what's going on behind the casing in the screen, so that we can get a good assessment and only seal off what we need to seal off to effectively reduce the contaminants coming into the well. So once we've done our well profiling, then what we're going to do is we're going to come up with a plan to modify the well. And that's going to involve various techniques and methods to seal off the problematic zones, or those zones where we're getting high levels of contaminants coming into the wells. And it's best if there's lithostratigraphic controls that we can deal with, and then we can go in there, and sometimes something as simple as swedging that zone or putting a seal on there. Sometimes you have to get in there with a packer and pack off some zones, and then squeeze some concrete out into seal those up, or some grout to seal those up. And so, but there are some different techniques. Fractured rock wells can be a little different. Sometimes you gotta pull the shallow casing out or drill it out and get in there and extend the seal down to address certain fracture zones and identify where the contaminants are coming in these fracture zones, and seal those off. So there's a variety of tools we need. I like to have video too to help guide me, especially on fractured rock wells. It can be a big boost, but between the tools that are at our disposal and the discrete sampling techniques, we can come up with a good plan if things are controlled either by a fracture or a lithostratigraphic unit, or they are vertically defined somehow. That is where well profiling and modification works best. We have done some of the profiling where we've gone in and looked at arsenic, for instance, and it was pretty evenly distributed throughout the well. That is not a situation where well modification can work. If you have well-defined zones that you can identify during your profiling process, then that is a situation that is just made for well modification. So, all right, so let's look at some of the. This is well profiling in the field, so that's some of the geophysical tooling out there, doing some sampling. This is in Northern California, I believe. So so that's kind of what the setup looks like to get out there. So in this particular case, we were running some geophysical tools, an EM flow meter, and doing some sampling as well, and in some relatively shallow wells out here. So, but we were able to define some specific zones, and in this case, we were doing things up front as part of a well design. So we actually designed the well to preclude the bad water, the contaminants, and so that's another case for well profiling right up front when you're doing your test well, is to actually design the well up front. But we can go in and we can do this retroactively as well, and so it's a good technique. And we've actually, instead of doing zone testing, we've actually gone out and started doing the well profiling. Gives you a much more granular look at the well, where the water's coming in and where the contaminants might be coming in, and allow you to design the well right up front. Really no additional costs in doing that. Maybe some, yeah, I mean, other than the profiling, which is actually taking the place of zone testing, traditional zone testing, hideously expensive, and you don't get much detail. You're able to do 2 or 3 zones maybe. With this technique, for about the same price as doing traditional zone testing, we can get a lot more information, design a lot better well. So it works there, and it works after the fact too in existing wells. So where it works, it's a great technique. All right. This is kind of what things look like. This is the flow profile on top here. This is actually looking at, I believe that's arsenic levels there. So you can see kind of where the arsenic is tied into some hot lithostratigraphic units there. And so you're able to design a well, or do a modification on this well, by knowing specifically where the contaminants are coming in and sealing those zone off. So that's just an example of some of the output. This I believe is a USGS program, whose name escapes me right now, but hydroanalyzer, something like that. But there are tools out there available for this, and so you graph it up and you plot it up, and you can plan it out and come up with your technique to seal these particular zones off. All right, so cost comparison. A new municipal well is going to cost somewhere between $350,000 and $1.7 million. Now, we're talking typical ranges, and that is a pretty wide range right there. But you can have, real small water systems that can do cheaper wells, and you can have some bigger ones that are a little more complex and go beyond this. But those are cases that are outside the norm, and still you have a pretty wide range. It's going to vary based on the depth of the well, the size of the well. Obviously, an 8-inch well is going to cost you, a 400-foot 8-inch well is going to cost you a whole heck of a lot less than a 16-inch well that goes to 1,000 feet. So clearly a lot of differences. Construction materials, if you're going all stainless steel, then that's going to add to your costs as well. Although I'm generally pretty much a stainless steel guy these days for pretty much everything, because it pays off in the long run. That's a topic for another show again, but those costs. But you can see there's a wide variation there. But on the upper end, well, it's certainly a significant cost. That's for sure. So a treatment system now, like I mentioned, there are multiple components to a treatment system. There's the upfront capital costs that can range from $100,000 to $1 million or more, and some of these more expensive systems is like a it can bump up from $1 million depending on how much throughput you have, is often the deciding factor there. A reverse osmosis is going to be more expensive than just a green sand filter, for instance. So there's a fairly wide range there. However, the catch is, with like comparing it to a new well, where most of the costs are the capital costs up front. With the treatment system, there's the ongoing operating costs, and those can range from $30,000 to $100,000 per year or more. Obviously, with something like a reverse osmosis system, where you're dealing with the brines and the disposal costs or treatments of those brines, that can start to add up a lot. So that's really the trick with the treatment system, is not only do you have some pretty hefty capital costs up front, but the ongoing costs to maintain that system are pretty high as well. And as I mentioned, also, it may also include the cost of a new operator. So you may have to hire a higher level operator in order to operate this system. The more complex the system, the higher the level of certification of the operator you need to have, and a higher level operator is obviously going to command a higher salary. So you need to factor that in as well. So typically a treatment system is going to be your most expensive option. And even though it's the default option for most people, it is going to be your most expensive option. All right, so in comparison purposes, let me see here. Okay. Um, Well profiling modification, the cost of a well flow characterization and vertical profiling of contaminants can generally range from $20,000 to $45,000 if you're doing some additional geophysics and characterization. There's a lot of stuff we can do. We can do casing integrity testing, but those are all going to bump your costs up. So 20,000 to 45,000 to assess the well to determine um, one, if it's going to be a candidate for well modification, and two, then what zones are problematic and how would we tackle those zones to modify the well to reduce the contaminants coming into the well doing the modification. The cost to modify the well based on the well characterization can range from $35,000 to $75,000 in a typical range if you're doing swedging, a little bit of packer, and pumping and grout. If there's more involved, more extensive zones, then it can go up from 75,000, but usually we don't see that running much more than that. So it's we've gone in and done some pretty extensive work with some fractured rock wells where we sealed off fractures down to 300 feet and stuff, and it did not get up into that range. So that's generally what you're looking at. So to kind of sum things up, well replacement 350,000 to 1.7 million. Treatment systems, the capital cost component, 100,000 to a million or more, with annual costs of 30,000 to 100,000 or more. And well profiling and modification, profiling can range from the 20 to 45,000, and modification of the well, then based on the profiling, can range from 35,000 to 75,000. So we can clearly see that if well profiling and the modification is an option available to us, and like I said, you have to have certain characteristics in the well where this is going to work. It needs to be defined zones where the contaminants are coming in. So lithostratigraphic zones are going to be important. Then certainly well profiling and modification are by far and away the most cost-effective method, and it's generally once you're done, you're done. There are no maintenance costs other than doing your normal well rehab. So really the well profiling and modification where it works is really your most cost-effective option. All right, so that then is let me hold on a minute here. All right, so try to get rid of that. That is our show today, and so hopefully you got an understanding of how well modification is certainly a viable technique where it's appropriate, and we find that in most cases there's going to be a vertical component that you can define where this can work. Sometimes it doesn't, so you take the risk of running the profiling and saying this just is not going to work in our case. So you spent that money, but it's still valuable information. So you can use that information. So as opposed to a treatment, which is really most expensive option with ongoing costs forever. So there we go. All right, so if you want to be a guest on Groundwater Talk Live in the future, I love to have guests on. We had one on last week. We got some guests coming up. This is my Book Me page that you can sign up to come on the show. If you're an expert in a particular groundwater topic, I'd love to have you on and have a discussion. So do that. And thank you very much for watching. Don't forget to subscribe to the Groundwater Guy YouTube channel. Hit the bell. We do this every Thursday at 11 a.m. Central Time. So I appreciate you all and all the comments. Thank you very much, and I will see you next week.